Welcome to Brain Vision.
All right, guys, let us start with the answer of this question. So, first of all, the reaction is CH4 plus 2O2 and reaction sign CO2 plus 2H2O, which is also the real reaction, the reaction that we consider because we don't have the data for CH4 like enthalpies and the entropies uh, at certain temperatures. Uh, so KPS, etc. in the textbooks. We need to find them somehow. Uh, so it should not be a problem for us. So let us go with part A of this question. The enthalpy of reaction can now be determined using H bar is equal to sigma NP into HF bar dot plus H bar minus H bar dot for P, and then we've got the summation sign NR multiplied by HF bar dot plus H bar plus minus H bar dot for R, where NS are the moles of each components and HF, H and H bar dot are the enthalpies of formation at 2500 Kelvin and 298 Kelvin respectively. The last equation in our case using the data from table A18 and A26 and other sources is H dash R 8 HR bar is equal to 1 into minus 393,520 plus 131,290 minus 9364 plus 2 into minus 241 point 241,820 plus 108,868 minus 9904 minus minus 1 into minus 74850 plus 181,992 minus 10018 minus 2 into 0 plus 87057 minus 8682 kilojoules per kilomole. The enthalpy reaction is therefore H bar R is equal to minus 811,184 kilojoules per kilomole. Now let us move towards part B of this answer. The enthalpy of reaction value at 2500 Kelvin can be estimated by using Kp values at, for example, uh, 2450 and 2550 Kelvin, the closest of the two temperatures to 2500 Kelvin in the enthalpy data tables. So the Kp value can be calculated using the enthalpy and entropy data, that is Kp is equal to E raised to power minus delta G asterisk of into T divided by Ru into T. So we know that the delta G steric function of T is equal to VH2O into G bar steric H2O of T plus VCO2 into G bar steric into CO2 function of T, CO2 function of T minus VCH4. Let me write this in the next line, minus VCH4 into G bar asterisk function of T minus VO2 into G bar asterisk O2 function of T, and also VH2O is equal to 2, VCO2 is equal to 1, VO2 is equal to 2, VCH4 is equal to 1. And by using the definition of the Gibbs function at 1 atm pressure, G bar asterisk, that is the Gibbs function, is equal to H bar function of T minus T into S bar asterisk function of T. So now we've got G bar asterisk H2O at 2450 Kelvin is equal to minus 241,820 plus 106,183 minus 9904 minus 2450 multiplied by 275.201 kilojoules per kilomole is equal to minus 819,783 kilojoules per kilomole. 783 kilojoules per kilomole. Similarly, we've got G bar asterisk for CO2 at 2450, and we have minus 393,520 plus 128,219 minus 9364 minus 2450 into 321,566.566, and that is equal to minus 1062502 minus 1062502 kilojoule kilojoules per kilomole. Then we've got G bar steric for O2, and that is 0 plus 85112 minus 8682 minus 2450 multiplied by 276.424 kilojoules per kilomole is equal to minus 600809 kilojoules per kilomole. Then we've got G bar steric for CH4 at 2450. This is also at 2450 Kelvin temperature. Now minus 74850 plus 177046 minus 100118 minus 2450 multiplied by 325.248 is equal to minus 704,679 kilojoules per kilomole. So by substituting the values above, we get delta G steric function of T is equal to minus 795,771 kilojoules per kilomole. So the natural logarithm of the equilibrium constant for T 2450 Kelvin would be Ru is equal to 8.3145 kilojoules per kilomole Kelvin. So ln Kp at 2450 is equal to 39.065. Alright guys, now we will repeat the same exercise for temperature 2550, and we will get and this for let us write here the temperature first, for which we are at 2550 Kelvin. We get G bar steric for H2O is equal to minus 241,820 plus 111,565 minus 9904 minus 2550 multiplied by 277.34 is equal to, that is equal to minus 847412 kilojoules per kilomole. Then we've got G bar steric for CO2 is equal to minus 393,520 plus 134,368 minus 9364 minus 2550 into 324026, and that is equal to minus 1094,782 minus 1094,782 kilojoules per kilomole. Then we've got G bar steric for O2, that is 0 plus 89004 minus 8682 minus 2550 multiplied by 277.979 is equal to minus 628,524 kilojoules per kilomole. Then we've got minus 74 minus 74850 plus 186,954 minus 10018 minus 2550 into 329.216 is equal to minus 737.415 kilojoules per kilomole. By substituting the values above, we get delta G asterisk T minus 795 143.2 kilojoules per kilomole, so that the natural logarithm of the equilibrium constant at temperature 2550 Kelvin would be Ru is equal to 8.3145 kilojoules per kilomole into Kelvin. Natural log Kp is equal to 37.503. Now, after exhausting calculations using the equation, we have ln Kp 2500 over Kp 2450 is equal to Hr bar divided by Ru into 1 over T1 minus 1 over T2 is equal to natural log Kp 2550 minus natural log Kp 2450, where Ru respond represents the ideal gas constant T1 and T2, lead us the estimated value of the enthalpy of the reaction, which is H bar R is equal to minus 811,378 kilojoules per kilomole. Despite the large temperature difference between T1 and T2, the two results are also almost identical. The agreement between the two results would be ever better if a smaller temperature interval were used. So, guys, the answer to this question for part A and for part B are, this is for part B, whereas the answer to part A is this. So these are the two answers for this question. I hope you have easily understood all the calculations and the formulas. Thank you very much.